So, dear friends, now as I was promising you that we will soon try to solve a problem so that you get more clarity, and there is every possible chance that because of all those equations and terms, you may lose insight of the airplane. So as I promised that we will be doing some problems so that you get physical feel for whatever equation, whatever expression we have developed. Today we will be solving a problem on stability. As this course title is Stability and Control, so today we will be solving a problem on stability so that you get a feel. Before I solve this problem, let me again reiterate, the role of wing is not to provide stability. Role of wing is to give enough lift. That's very large aspect ratio or large wing area. But who provides the stability? Whose responsibility is to give stability is the tail. For longitudinal stability, it is horizontal tail. For directional stability, it is vertical tail. So we are now talking about longitudinal stability. We'll try to solve a problem of longitudinal stability and try to see how whatever the expression we have developed, how can we very conveniently use it for solving a problem. Okay? So let's start with the problem. And this problem I have given from a book which is Flight Stability and Automatic Control, which is a second edition by Robert C. Nelson. It's a very good book. I am not campaigning for this book, but it's my duty to tell you because I follow many books. One of those is Flight Stability and Automatic Control by Robert C. Nelson. And this problem is from that book only. So we'll be now using this opportunity and to use this beautiful example and try to communicate more on stability, right? So what is the problem? Let me define the problem. The problem says the wing, fuselage, pitching moment characteristics is given by Cm AWW and Fs means wing fuselage as minus 0.05 minus 0.0035 alpha. And please understand, this part is what and this part is what. That is more important before you solve a problem. What does it say? If I try to understand by drawing a diagram, I say there is a fuselage has been designed and wing has been designed, okay? And some CG, we'll soon know what is the location of CG of the aircraft is given. Now, the Cm characteristics is given by this for a wing fuselage combination. This is the fuselage and this is the wing. So do you think it is statically stable? How do I check? I write this like this. Cm wing fuselage is minus 0.05 minus 0.0035 alpha. And I try to understand through our understanding of the expression, we write Cm equal to Cm naught plus Cm alpha into alpha. So if I compare these two things, what is Cm alpha? Cm alpha is coming out to be minus 0.0035, and for this you can assume that this is per degree, okay, as per the problem states. And what is Cm naught? Cm naught is minus 0.05. So this is the characteristics of pitching moment, and we are seeing that this is only for fuselage and wing, and the expression after whatever plane has been designed for wing fuselage, it is something like this. And when I try to interpret the way we have understood, we have seen that by comparing I find Cm naught is minus 0.05 and Cm alpha is minus 0.0035 per degree. Okay, now let us see what is the meaning of that. Are we happy with it or not? So if I try to plot Cm versus alpha, right? What type of plot or variation you really expect for a stable airplane, statically stable airplane, and which can be trimmed at positive angle of attack? We all know it should be something like this. That is, slope should be negative. That is, slope Cm alpha should be negative and Cm naught should be positive. Then only I can trim at positive alpha for most of the cases, right? This part is clear? But if I try to see this here, yes, Cm alpha is minus 0.0035, so Cm alpha less than 0 is satisfied. So this configuration, whatever is been given for fuselage and wing, this is statically stable. To what degree stable? That is decided by the Cm alpha. So as far as static stability is concerned, this configuration is statically stable. No doubt about it, because Cm alpha is negative, and that is the condition here. But if you want to trim at positive angle, then what is the condition? That Cm naught should be greater than 0. But what is happening here? Here Cm naught is less than 0. So I won't be able to trim this airplane at positive alpha. That is, if we see here, Cm naught, some negative value here, let's say this is minus 0.05, and statically stable, so the line will be something like this for this variation. So what is the problem? Although this is statically stable, but I cannot trim it at positive angle of attack. It is having a Cm equal to 0 at negative angle of attack. So I don't want that, right? So problem definition starts from here. So what is the obvious question for the problem? I want to trim this airplane at a particular alpha, positive alpha, and I may require Cm alpha little more, because I may require to design an airplane for a particular value of stability, static stability. So I may have decided number, Cm alpha should be minus 0.5, minus 0.1, minus 0.8, depending upon what sort of airplane I'm designing. So this problem has been designed to give you that concept of Cm naught and Cm alpha. So let us see what is the problem. Once you have understood this, now we will read the problem and try to understand what is the problem. Problem is, although wing fuselage is giving a statically stable configuration, but we want to design a tail such that Cm wing, fuselage and tail gives a combination which should be something like this. This is a problem from Nelson, so please, you can read it. Plus 0.15 minus 0.025 alpha. So what is the difference now? Try to appreciate. The wing fuselage was like this, where Cm wing fuselage is minus 0.05 minus 0.0035 alpha. That means Cm naught was minus 0.05. Now we want to design a tail for the same airplane so that overall Cm naught becomes that is Cm naught wing, fuselage and tail becomes 0.15, and Cm alpha wing, fuselage and tail, it becomes minus 0.025 per degree. So what is the problem as a designer to a designer? I should do something so that Cm, earlier it was something like this. This value was minus 0.05. And now what I want it should be like this, where this becomes 0.15 and the slope also becomes minus 0.025 compared to the slope it was here minus 0.0035. Okay? So not only we are changing the Cm naught value to get a positive alpha trim, but also we have to make it more statically stable. That is the problem. Who will do that? We all know this is the role of the primary role is of the tail, horizontal tail in this case. So we'll be finding out what is that tail area required to change this Cm alpha from minus 0.0035 to Cm alpha equal to minus 0.025. Similarly, by giving some tail setting angle, okay, how can I change Cm naught of the whole aircraft from minus 0.05 to plus 0.15? That is the question. Okay, 0.15. This is actually 0.15. Let me correct it. Okay, this is the value. This is we are designing, or we want to go for it. So let me repeat again, and in a very small but crisp manner. What is the final problem to us? It was given Cm wing fuselage was minus 0.05. So Cm wing fuselage was minus 0.05 minus 0.0035 alpha. The new, what I want, Cm wing fuselage and tail to be 0.15 plus minus 0.025 alpha. So this is the problem. How this can be done? Through design of tail. Design of tail means what? What is the tail area? What is tail setting angle? Where should I locate the horizontal tail? Or what is the tail volume ratio I look for? So these are the questions that will come into our mind. Okay? So this is the basic simplified problem. Now how do I approach it? Okay? That is the question. From this, you can understand how much delta Cm naught you require from tail. Required from horizontal tail. How much it will be? I want 0.15 Cm naught here, 0.15. So it will be 0.15 minus already available minus 0.05. So this will be equal to 0.20. Right? How much delta Cm alpha I require? See again, if I see it from here, minus 0.025 minus 0.0035, and that is equal to minus 0.0215 per degree. So again I repeat, this is the additional Cm naught and Cm alpha will be required to convert the pitching moment characteristics from this minus 0.05 minus 0.0035 to plus 0.15 minus 0.025. So how much we have to do? We have to generate Cm naught 0.2 and Cm alpha additional should come 0.0215. And who will provide this? The horizontal tail. And how do I get it? By appropriately selecting the horizontal tail area and the location of horizontal tail from the CG of the airplane, or together we call tail volume ratio. And for Cm naught, we also will try to use tail setting angle. That is, if this is the horizontal tail, instead of having like this, if I set it at negative angle of attack, you know, even at alpha equal to 0, there will be force downward, which will give a Cm naught positive, which we are already knowing. Now we'll be using those formula to solve this problem. Okay? Let us go back to those formula, whatever you have realized. So let me erase this now. Let me write the formula Cm alpha tail, which already you know, neta VH CL alpha tail into 1 minus d epsilon by d alpha. Okay? Let me repeat again. This is Cm alpha tail, which is neta. For this example, we'll take neta as 1. VH is tail volume ratio. CL alpha tail is the lift cut slope of the tail based on the tail area. And d epsilon by d alpha is the downwash gradient. And you know, already in first course you have seen d epsilon by d alpha I can compute as CL alpha wing by pi aspect ratio. Approximately this is I'm taking equal to 1. And if you see here, In the initial slide I have given, and now also you could see here, CL alpha wing is 0.07 per degree, and d epsilon by d alpha, I can use it. This also will be aspect of the wing. If I put those number, I will get, this is 2 into 0.07 into 57.3, because I have to convert into radian, it was per degree, where pi aspect ratio is 7.3, and this will get value as 0.35. So d epsilon by d alpha is purely mechanical. You put those numbers, CL alpha wing, you could see here, it is given CL alpha wing as 0.07. When I write CL alpha wing, please understand one thing. Here I have written CL alpha wing and fuselage. So there is an approximation. We are neglecting the contribution of fuselage, because this d epsilon by d alpha in the first approximation is primarily because of the wing. Okay, no fuselage is there. Okay, but there's an assumption here. You can take it that fuselage CL alpha is very negligible, so we are neglecting it. Okay, as a first approximation. So I know now this term, CL alpha tail, you see here, CL alpha tail is given 0.073 per degree, but note this is based on tail area, right? That is why you see here in the formulation, in the VH, it is ST LT by S wing C bar wing. This ST is here. So CL alpha tail is 0.073 per degree. And let us now see what will be the VH. So VH will be, if I solve this equation from here, VH will be equal to Cm alpha tail required. How much Cm alpha tail will be required? We have seen already. This is how much? If you check, it will be around minus 0.0215. Let me write this then so that I can explain it. Divided by 1, then 0.073 into 1 minus 0.03, 0.1 minus 0.35. Where from this has come? Let me again check. 0.0215 by 1, 0.073, 1 minus 0.35. You could easily see from here, from this expression, I could write VH equal to Cm alpha tail divided by, this is minus sign, divided by neta, which is 1, CL alpha tail to 1 minus d epsilon by d alpha. Okay? Now you will ask me a question, where this minus sign has gone? So we have to be very, very clear that when you are computing this, there is a minus sign here, so I put a minus sign here. Okay? Now it's clear? Again, let me repeat. Cm alpha tail is neta Vs CL alpha tail 1 minus d epsilon by d alpha. You know how to calculate d epsilon by d alpha because this is a contribution from wing, right? And this is 2 CL alpha wing by pi aspect ratio wing. And you know the value is 2 into 0.07. We have multiplying by 57.3 because 0.07, which is CL alpha of the wing, is per degree, so you have to convert to per radian. So we have multiplied by 57.3 and then divided by pi aspect ratio wing, and we have got d epsilon by d alpha as 0.35, which we have plugged here, correct? Now, from this expression, I can write VH equal to minus, so let me make it neater. This is minus is here, minus Cm alpha tail by neta CL alpha tail 1 minus d epsilon by d alpha. Here I have put those number, and I have got the VH value as something like, how much? 0.453. I have been telling in many lectures, when you are designing an airplane, VH should be around 0.5 to 0.8. That's a good initial guess number, right? So this is the typical value of VH. And what is VH? Let us also understand before we use this number. So let me erase this part. what was VH? What is VH? As a designer, will like to understand it. Remember, if this is the center line of the airplane, and if this is the CG of the aircraft, and if this is the tail, and this is the AC of the tail, right? And this is the S tail area, then this distance is called tail moment arm for horizontal tail, LT. And if you see LT here, it's 14.75 feet. Okay? And then what is VH? How VH is defined? VH is defined as ST into LT by wing area into mean aerodynamic chord of the wing. So this ratio, ST-LT by SW, for this problem is 0.453. So what is the result? Result is, if I want to change Cm alpha to 0.025 to minus 0.025, then I need to ensure that the tail volume ratio is 0.453. Is it clear? I repeat again, what is the interpretation of this result? Is that if I want to change Cm alpha of the aircraft, that means wing, fuselage, and tail, to minus 0.025, right, from minus 0.0035, then I need to have VH equal to 0.453. Correct? Okay? What next for a designer? Let us try to understand little more. As VH equal to 0.453, and we have already LT equal to 14.75. Also we have SW is equal to wing area somewhere, it's a 178 feet square. Sorry for using feet unit. And CW is equal to 5. So what I can do, I can use this relationship VH equal to ST-LT by SW-CW and get the value of ST. And if you do that, you will get the value of ST as 27.3 feet square. Clear? Please, you should do yourself this calculation. If I commit some mistake or there's some printing error, I will not be held responsible. So it's very simple. You have to find ST. VH you know 0.453, so ST will be 0.453 into SW into CW divided by LT. So you'll get S tail area this much. So what is the final conclusion? If I want to increase Cm alpha of this configuration from minus 0.0035 to minus 0.025, then I need to put a tail area of 27.3 such that the AC of that tail is 14.75 feet aft of CG of the airplane. Is this clear? Or pictorially what I should say? I say this will be 14.75 feet, and this is the AC of the wing, and the S tail will be 27.3 feet square. And if it is done, and the aircraft still remain at the same CG location, then the Cm alpha of the aircraft will become minus 0.025, not minus 0.0035, right? And who has done this? It is the tail area has done this. For a designer, what he will tell, it is the appropriate tail volume ratio of 0.453 has done this change. Okay? Now, this is as far as slope is concerned, and static stability is concerned. Now I'll be talking about the trim, that is Cm naught. Remember the problem was wing fuselage Cm naught was negative, so we want it has to be positive here, and we realize that delta Cm naught, which is required, is around 0.15. So how do I get this delta Cm naught 0.15? Using the tail, primarily through tail setting angle. And that is the problem we'll be doing now. So let us again use those formula, whatever we have developed. Cm0 tail equal to Vh neta Iw plus epsilon naught minus It. Right? So It equal to is minus Cm naught tail by Vh neta Cl alpha tail. Here some Cl alpha tail will be there, no? That is why. Cl alpha tail, yes. And this is this minus Iw plus It. Okay, It we are finding out, so there is nothing required, minus epsilon naught. Okay, please be careful here. Initially I missed this Cl alpha term here. Cm naught tail as we have derived is Vh neta into this term into Cl alpha tail. So if I try to find out what is the tail setting angle It required, I can algebraically show that It will be equal to minus Cm naught tail by Vh neta Cl alpha tail minus Iw wing setting angle minus epsilon naught. I hope you remember what is wing setting angle. Okay. What is the value of Cm naught tail? How much Cm naught tail required? Is 0.15. Vh we know, neta we are taking 1. Cl alpha tail is also given here, right? Iw wing setting angle, Iw 2 degrees given here. Epsilon naught, right? How do I find epsilon naught? You know, for finding epsilon naught, you know, epsilon naught is 2Cl naught by pi aspect ratio, and Cl naught is given how much? Let us see, Cl at alpha equal to 0.26. So I put this value here, so epsilon naught is 2 into 0.26 by pi, and what is aspect ratio is around 7.3. So this gives you a value equal to 1.3 degree. Correct? This is the, why this epsilon naught is present? Because the wing is cambered. So even at alpha equal to 0, there will be a lift, and lift means there is a pressure difference between lower and the top surface. Lift means there is a difference between pressure between bottom and the top surface. So there will be vortices, and that will induce downwash. That is why epsilon at alpha equal to 0. So this is definitely a cambered aerofoil. You should appreciate that. So now if I put every value here, I can easily see It as minus 2.7 degree. It's straightforward. You can plug in all those values here. So you are getting It equal to 2.7 degree, and Vh required is 0.453. So this is the solution. So now to conclude, through this problem what we learned there is a wing fuselage combination which had Cm alpha negative. That means it is statically stable. That means most probably AC of the wing is, why most probably? If Cm alpha is negative for a wing fuselage combination, it is sure that wing AC is behind CG of the airplane, right? However, we wanted to increase static stability as well as we want to ensure that it can be trimmed at positive angle of attack. So we found out what is that tail size required, what is the tail setting angle required to ensure that now the Cm versus alpha for wing, fuselage and tail is what exactly we are looking for. Is it clear? This problem is only to give you a better feel for all those expressions we have developed.